As you guys have probably seen, AI can make decisions, it can respond to text, it can make movie recommendations, it can classify whether someone has cancer or not. And honestly, AI can do so much that people have been kind of freaked out by that. They've seen AI in movies like The Terminator, where you have AI going after and assassinating people, or they've read Hitchhiker's Guide to the Galaxy, where AI is like this mighty sage that makes complex decisions, to determine the future of humanity. It's crazy. So the question is, how does AI make decisions? And that's what we're going to focus on in this video. Now, the simplest type of decision is a binary decision, yes or no, and that's what we're going to focus on here. We're going to see how AI makes these simple yes or no decisions. And again, it all comes down to math. The yes-no model is called logistic regression, and it uses this function called the sigmoid function that outputs a probability between 0 and 1, and here's a graph fit. And basically you set a cutoff probability, and anything greater than the cutoff probability is yes, and anything less is a no. So that's how AI makes decisions in a nutshell. It's pretty simple, pretty basic. Here's the sigmoid function. The E is Euler's function, or Euler's number, which is a constant like pi, and the X refers to the matrix of all the inputs you're passing in, and the B is the beta. Those are the weights. So let's see how we get those weights. Again, like linear regression, you have to find the minimum of the cost function. Only this time it's a little different. In linear regression, the distribution of the error, it's Gaussian distributed. It has a normal distribution. Well, in this logistic regression, since the predicted value it's either a 0 or a 1, it can't have a Gaussian distribution, so we can't represent like the errors like based off that. We have to use a different function. So instead we use this cross entropy error function, which allows us to kind of more approximate the zeros and the ones. Okay, so where did this error function come from? I'm sure you're wondering. The cross entropy error function is kind of random. Well, it's the flipped version of the log of the maximum likelihood function. And the likelihood function, it finds the likelihood of a biased coin, so heads or tails, yes or no, where the probabilities of the two occurring things are different. So finding the maximum likelihood means finding the maximum likelihood where something's most likely to occur. And the log of the maximum likelihood function is the flipped cross-entropy function, binary cross-entropy function. So by maximizing the likelihood of an event occurring, by maximizing the log likelihood, the maximum likelihood function, it's the same as minimizing the log cross-entropy cost function for logistic regression. So how do you minimize this cross-entropy cost function? How do you find the best weights for beta, the weights? So if you recall in linear regression, we were able to take the derivative of the cost function and set to 0, and use the ordinary least squares method as the solution. Well, this is not the case with this new cost function, because it doesn't have a solution when set to 0. So instead we have to use a technique called a gradient descent to solve for the weights. And a gradient descent, it does not guarantee an exact solution. It gives an approximate solution. In gradient descent, you move in the direction of the minimum, and you get as close as possible without actually getting there. And it can be used with different functions besides this binary cross-entropy function. So you'll see it come up a lot more when we talk about neural networks and other deep learning models. And when using gradient descent, the general formula for updating a weight is this. So you have the new weights equals the old weight plus the learning rate times the partial derivative of the cost function with respect to the weights. And we're not going to use learning rate here, but we will in the future with like when we talk about neural networks. The learning rate is it's a constant, and you typically set it to 0.1. And if you're fine-tuning it, you'll set it between 0.1 and 0.0001. The tuning, it allows you to get a more accurate model. So if you're doing multiple epochs, you'll update that over time and see that. So in order to, there's the formula again. In order to find the partial derivative of the cost function with respect to the weights, you need to take 3 derivatives. You take the derivative of j, the cost function, with respect to y. That's the activation function. That's the sigmoid. Then you take the derivative of y with respect to the input of the activation function. So the activation function with your inputs, and then again the activation function here is the sigmoid activation function. And next you take it with respect to the weights, and once you have those 3 derivatives, you multiply them together, and that gives you the derivative of the cost function with respect to the weights. And that's how you do gradient descent with logistic regression. When we get into neural networks and more complicated uses of gradient descent, you'll find it's pretty much all the same, except you kind of change the activation function. So that's how AI makes binary decisions. It's just solving that sigmoid activation function and getting a result between 0 and 1 and deciding if it's a yes or no based on the cutoff value. And that's it. It's really cool. When you zoom out a bit, you'll find that AI, it's not really thinking. It's not like the Terminator or anything like that, or it's making these crazy, like it has like a personality or something like that. It's just doing an elaborate math problem.